Okay, so question number 3 in the 2013 midterm. In part A, we're told that the reliability of a valve depends on the reliability of the two O-rings that make up the valve. I'm guessing these O-rings are critical in the function of this particular gate valve that they speak of. And the question says that the O-rings themselves follow a Weibull distribution with parameters beta of 3.3 and alpha of 10,000 hours. So whenever you have a Weibull distribution, your random variable x captures a time until the failure of that particular part, in this case the O-ring. So x being Weibull with beta equals to 3.3 and alpha is equal to 10,000. And in part A, we are asked to find the mean and the standard deviation of our random variable x, or the average time until the failure for the O-ring. Having established that x follows a Weibull distribution, there's a formula for computing the expected value of x, and it's given by this. Okay, so I've pre-computed the number for you guys. Alpha is equal to 10,000, beta is equal to 3.3, and we have the gamma function. So once we compute all the numbers, we have 10,000 times gamma of 1.30. And let's go look up what that value is. So I have the gamma function table here, and I have highlighted when your gamma, or the value inside your gamma function, is equal to 1.3, then gamma of 1.3 is given by 0.897. So this is equal to 10,000 times 0.897, which gives us an average time until failure of 8,970 hours. Okay, so if I have a whole bunch of these O-rings, I can be sure that on average they will last about 9,000 hours. Part B, or before we go to part B, we also have to calculate the standard deviation of x. Okay, so let's calculate the variance of x first, or the sigma squared, and that is given by all of this. It's a long equation, but as soon as you can establish that a particular random variable follows a Weibull distribution, really it becomes nothing more than a computational problem. So I have here 10,000 squared. Let's fast forward here a little bit. Alright, so I plug in some numbers here, and we're left with gamma of 1.61 times 10,000 squared minus 10,000 squared times gamma of 1.3 all squared. Factoring out 10,000 squared, I have gamma of 1.61, which is equal to 0.894 from the gamma function table. And the gamma of 1.3 we had seen in part A, or when calculating the expected value of x, it was equal to 0.897. And computing this, we get 8,939,100. Obviously, to get sigma, or the standard deviation of x, we take the square root of 8,939,100 to get a standard deviation of 2,989.83 hours. Okay, so on average, every O-ring will deviate from the mean of 8,900 hours by about 3,000 hours.